happening in a vacuum. It seems like abstract math and, well, hard experimental physics are finally coming together in a big way.
That's absolutely the core theme here. Our mission really is to pull out the key insights showing how quantum science is now cracking problems we used to think were, well, fundamentally intractable. It's redefining reality. And you'll see, this whole shift hinges on these sophisticated mathematical frameworks.
Okay, so we've got three main areas lined up. First, how new quantum algorithms are solving these deep mathematical puzzles about symmetry. Second, how we're literally starting to measure the geometry of the quantum reality itself. And finally, what happens when quantum effects get bigger, scaled up?
Right, let's dive into the math first, because honestly, it underpins everything else. A massive step forward was developing quantum algorithms that can efficiently factor something called group representations. Now, think about symmetry like in a crystal or even musical patterns. Group representations are the complex mathematical language describing those underlying patterns.
Okay, I think I follow that analogy. So factoring these is key for understanding fundamental particles and stuff, but are you saying normal computers just choke on this?
They do, completely. Trying to factor these classically is, for all practical purposes, impossible, even for the fastest supercomputers we have. This 2025 work showed a clear, undeniable quantum advantage here. It's a breakthrough for solving these deep symmetry problems, which helps everywhere from particle physics to creating much better error-correcting codes.
And looking ahead, does this mathematical power feed into, say, future security?
Directly, yeah. There's a whole theoretical framework being built now for quantum-resistant encryption. They're using new mathematical ideas, things like one-way state generators. Okay. The point is, these are designed to be incredibly hard to break, even for the powerful quantum computers we anticipate down the line. It's about future-proofing our data.
Okay, so that mathematical bedrock allows for the next big thing you mentioned, moving from formulas to actually seeing the shape of quantum reality. We're talking about the first direct measurement of quantum geometry for electrons inside a solid material. That sounds pretty wild.
It really is a spectacular achievement. They did this in a specific type of material called the Kago metal. It's known for its very ordered geometric lattice structure. And quantum geometry, it describes the shape of an electron's wave function, often written as T psi a. We can now actually observe and measure this fundamental shape.
Okay, but what does that mean practically? Why should you, listening, care about the shape of an electron's wave function?
Well, because that shape fundamentally dictates how the material behaves. Measuring it is the key step toward actually controlling properties we care about, like superconductivity or magnetism.